Hello students, I hope all of you are doing well. So in this video, we will be revising magnetic effects of current. All these topics are there, one by one, we'll take a look at them, right? So we are starting with magnetic field. What is our magnetic field? If we have to define magnetic field is the influence around a moving charge or a magnet or a current carrying element, right? It is the influence around the current carrying element, right? Now magnetic field, it is denoted by B. Magnetic field is denoted by B. It is a vector quantity. It's a vector quantity, and the SI unit of magnetic field is Tesla. SI unit is Tesla, right? It is also given as your Tesla is also your Weber per meter square. Tesla is also Weber per meter square. Fine. Now if we talk about that, how which charges or which elements are producing magnetic field, so let us discuss. First of all, if we talk about your stationary charges or static charges, right? Static charges produces only electric field, produces electric field only, and it experiences only electric force. Electric force only, right? Then we talk about your moving charges. If we talk about moving charges produces magnetic field in their surrounding, and they also experiences magnetic force, right? So moving charges produces magnetic field, and apart from magnetic field, obviously your electric field produces magnetic field and electric field, and it experiences magnetic force and electric force, right? Last, if I talk about your current carrying element or current carrying wire, so current element. If we talk about current carrying element produces magnetic field only. It produces magnetic field only, and it experiences magnetic force only. Now, why we are saying that current carrying element produces magnetic field only? As we consider a magnet, if we consider a wire, a current carrying wire, current is flowing due to the electrons, current is flowing due to negatively charged electrons, right? So due to these negatively charged electrons, motion of negatively charged electrons, your magnetic field is produced. But as a whole, this wire is a neutral. As a whole, this wire is neutral, and because it is neutral, therefore there is no electric field, right? So a current carrying element produces only magnetic field. So this is about the initial part of magnetic field. Now the question arises, second, okay, current carrying element is producing magnetic field. The question arises, current carrying element produces magnetic field. How much magnetic field? So that question is answered by Biot-Savart law. Biot-Savart law tells us about the magnitude of magnetic field produced by current carrying element. Let us see. Yeah. So next we are talking about your Biot-Savart law. What does Biot-Savart law say? Let's consider a wire is there through which current I is flowing, and we consider a small element of length dl. A small element of length dl. At a distance of r, a point P is present. Now over here, this r, the position vector of this point P, is making an angle of theta with the current element over here, and dl, this current element direction, is always taken as the direction of current. So what we are saying, direction along current. Fine. So the condition, the situation we have is a wire is there through which current I is flowing. We have considered a small current element dl, which we also says idl as the current element, and at a distance of r, a point P is present. The position vector of this point P, r vector, is making an angle theta with dl, right? So Biot-Savart law, according to Biot-Savart law, the magnetic field at point P, dB, is given as, dB is equals to mu naught by 4 pi I dl sine theta by r square, right? This is magnetic field at point P due to the small element, due to the small current carrying element. Now over here we can write this in vector terms also. In vector terms, what can we write? dB vector is equals to mu naught by 4 pi I dl cross r by r cube, dl cross r by r cube. This is your Biot-Savart law in vector form. What are the terms over here? If you notice carefully, mu naught is basically permeability of free space. It is the proportionality constant. It is your permeability of free space, right? And its value is, mu naught value is 4 pi into 10 power minus 7 unit Tesla meter by ampere, right? Mu naught by 4 pi, I is the current, dl cross r. In vector form, this is the cross product of your length vector and your position vector. So dl cross r by r cube. This is your in vector form, right? Now over here, so we have these relation. This is Biot-Savart law in vector form. Fine. If we talk about direction of magnetic field, how do we find out direction of magnetic field? So as you can see, magnetic field is coming due to the cross product of your dl and r. So that means we can find out direction given by right hand thumb rule for cross product of dl cross r. dl direction is taken along the direction of current, and dl cross r, if we do dl cross r, our thumb is pointing in inward direction. That means magnetic field at this point P is inward. Cross circle is used to represent inward direction. So dl cross r, your inward direction is coming, right? So this is all about your magnetic field due to current carrying element, right? This is our Biot-Savart law. Apart from this, as we know that this current is flowing due to the moving electrons. This current is flowing due to moving electrons, and we know that moving charges produces magnetic field. So can we write down magnetic field due to moving charges? Let us see. Magnetic field due to moving charges. Let's say a charged particle Q is moving with a velocity of v, and at a point P which is present at a distance of r, the position vector is r vector. So magnetic field at point P due to this moving charge particle is given as B is equals to mu naught by 4 pi. In place of ideal, you will get Q into V, mu naught by 4 pi QV sine theta by r square. This is your magnetic field due to a moving charge particle. We can write it in vector form also. What can we write? B vector is equals to mu naught by 4 pi QV cross r by r cube, right? This is your magnetic field due to a moving charge particle. This relation we can keep in mind. So the relations which we have to consider, we have to keep in mind. I am highlighting all of them, right? Direction, in this case also, if we have to find out direction of magnetic field, how we will get it? Cross product. Basically it is B, direction is coming from V cross R. V cross R, again it will be in inward direction only, right? Considering that this is a positive charge, obviously considering that this is a positive charge, then it will be V cross R. That means it will give us in inward direction. Fine. So right now we have discussed about your Biot-Savart law, and if we have to find out, this is Biot-Savart law gives us magnetic field due to small element. What if we have to find out due to large wires? Then in that case we will be integrating this. We will be integrating these results and then finding out magnetic field. So we'll see next, we'll see your application of Biot-Savart law. That is, so we have done magnetic field, Biot-Savart law, application of Biot-Savart law, magnetic field due to current carrying wire, finite wire, infinite wire, semi-infinite wire, and magnetic field due to circular coil. Let us see. Okay, So next we are discussing application of Biot-Savart law. In application of Biot-Savart law, we are seeing magnetic field due to straight current carrying wire. We have taken three cases due to a finite wire, infinite wire, and semi-infinite wire. First of all, let's focus on finite wire. What do we mean by finite wire? That a current carrying wire is there through which current I is flowing. At a distance r, a point P is there. Now the line joining the edges to the point P are making angle theta1 and theta2 with the wire, right? So magnetic field due to this finite wire is given as B is equals to mu naught I by 4 pi r cos theta1 plus cos theta2. This is our magnetic field due to finite wire. Be careful with the angle theta1 and theta2 are taken with the wire. Fine. Next, if we talk about your infinite wire, what do we mean by infinite wire? Infinite wire basically implies that compared to this distance r of the point P, compared to this distance r of point P, the length of the wire is very large. That is your infinite wire. Magnetic field in this case is derived from this result itself. Magnetic field in this case is derived from this result itself. When we try to join the point with the edges, basically theta1 and theta2 over here will come out to be 0 degrees. Right? So theta1 and theta2 comes out to be 0 degree, cos 0 plus cos 0 will get 2 over here. So finally our result in this case come magnetic field mu naught I by 2 pi r. This is magnetic field due to infinite wire. In question, it will be termed as long wire. In many question, it is not said specifically infinite wire. It's simply said long wire. So we have to consider our infinite wire, the result for which is mu naught I by 2 pi r. Next, if we take a look at semi-infinite wire. Semi-infinite wire is basically, as you can notice, in this case, theta1 value will be coming 90, whereas theta2 value will be coming 0, and due to that the result that we get is B is equals to mu naught I by 4 pi r, right? So these are our results. Let's see, let's highlight them. These are the results that we have to keep in mind. Mu naught value is 4 pi into 10 power minus 7. In question, obviously it will be given to you, but we can keep in mind. So these are the results. Now if we talk about, these are magnitude of the magnetic field. If we talk about direction, how do we find out direction of magnetic field due to straight wire? So the method is right hand thumb rule. Right hand thumb rule due to straight wire. How we do it? Your basically finger should be straight, thumb should be perpendicular to the finger. Keep your thumb in the direction of current. Keep your thumb in the direction of current and take your fingers at that point. The palm will be facing towards the magnetic field. So I'll show you. For example, over here, thumb in the direction of current, finger should be straight, and take your fingers at point P. When you take fingers at point P, the palm is facing in inward direction. So the magnetic field at point P is inward. This is the methodology that we use for finding out magnetic field due to straight wire. There are many methods, are used. One of them I have discussed. You also please follow one of them and practice your question accordingly. Okay, moving ahead, one last point that we should know is about your magnetic field lines due to straight wire. So if I have to draw magnetic field lines due to straight wires are concentric like this. These are concentric circles, magnetic field lines. If we draw it, it will be like this. Right? Concentric circles are the magnetic field lines due to a straight current carrying wire. Fine. Let us move ahead. So we are done with magnetic field due to straight current carrying wire. Next, let's move to your magnetic field due to circular coil. Okay. The next that we have is magnetic field due to circular coil. Three different cases are there. I have drawn it. And now one by one we'll take a look. First of all, magnetic field due to circular coil at the center point. If we talk about at center point, what we have? A circular coil through which current I is flowing and its radius is r. So magnetic field at center is given as mu naught I by 2r. All these results are derived from your Biot-Savart law only. So magnetic field at center due to a circular coil is mu naught I by 2r. Now if let's say that number of turns over here are n, then magnetic field will become what? Mu naught Ni or mu naught I by 2r into n, right? Next, if we talk about, so this is our first relation. Next, if we talk about your magnetic field due to a arc, a circular arc. So in this case, magnetic field at the center point, this arc is subtending an angle of theta. So magnetic field at center point is given as mu naught I by 2r theta by 2 pi. Theta by 2 pi. This is the magnetic field due to circular arc. Fine. Next, if we talk about magnetic field due to circular coil at a axial point. Axial point, on the axis a point P is present at a distance of x. So what is your magnetic field given as? B is mu naught I r square by 2 times r square plus x square whole power 3 by 2. This is the relation, somewhat is same sounding as what we discussed in our gravitation and your electrostats also, but there are some differences. First of all, this is the result, mu naught I r square by 2 times r square plus x square whole power 3 by 2. This is our relation, magnetic field at axial point due to a circular coil. Over here, this is due to one turn. If let's suppose total n number of turns are there, so we can write it as this will be n times, right? This is about magnitude. What about direction? So for direction, we have the rule for circular loop. What we do is we change little bit what we used in our straight wire, we changed it. What we do is, in this case, we turn our fingers along the direction of current. We turn, so fingers straight, thumb should be perpendicular. Turning the fingers along the direction of current, the thumb will give you the direction of magnetic field. So as you can see, if I turn it over here, the thumb is pointing outward. So at this point, magnetic field is in outward direction. Fine. In this case, if I see turn the fingers along the direction of current, the thumb will give the direction of magnetic field. Turn it, thumb gives inward direction, cross circle. Fine. In this case, if we see, the current is coming like this, and current is coming, so from this side person, it is your reference dependent. So if someone is observing from this side, it will be your current is anti-clockwise. If someone is observing from this side, it will be your clockwise. Anyways, so now over here, current is flowing like this. So let us turn our fingers along the direction of current. Thumb is pointing towards right. So the magnetic field at this point, P is towards right. Similarly, at this point also it will be towards right only. Right, it is magnetic field direction is toward right only. If we plot a curve, for magnetic field versus x, if we plot the curve comes something like this. This is the curve that you will be getting. Maximum will be at the origin. Fine. So I hope all these results are clear. Results are important. You must have clarity in your mind what are the results and how to use them. Fine. Let us move ahead. Next, we have to discuss your magnetic field due to solenoid and magnetic field due to toroid. Yes. So the next thing that we have to discuss is magnetic field due to solenoid and toroid. First of all, one by one, we'll take a look, right? So solenoid, what is your solenoid? Whenever a circular coil is tightly wound, and many turns are there, then we term it as your solenoid. Now over here, the result that we'll be writing, that will be for ideal solenoid, What do we mean by ideal solenoid? Ideal solenoid means basically, if let's suppose that the total length of solenoid is L and the radius of the turns are R. When your length L is very, very large as compared to your radius, we term it as ideal solenoid. The result for this is given as magnetic field inside solenoid is mu naught Ni. What is small n? Small n is number of turns per unit length. Number of turns, if total number of turns over here are capital N, the length is L, then small n is number of turns per unit length, right? So this is the magnetic field due to a solenoid inside, mu naught Ni. Now if you will observe over here, the result that we have written, this result is basically a uniform magnetic field. In a ideal solenoid, inside the solenoid, magnetic field is uniform. How we find out direction? Turning our fingers along the direction of current, thumb gives us direction of magnetic field. So inside ideal solenoid, you get a uniform magnetic field. And outside it is 0. B is 0 outside for your ideal solenoids, it is 0, and for inside it is uniform and the magnitude is mu naught Ni. right? Fine. Let us come next to our toroid. What is a toroid? As you can see, the coils are turned such that the radius of this turn, complete circular, is capital R. The radius of the coils are your small r. Now for over here, we take the consideration, the situation is that this capital R is very large as compared to small r, right? So the magnetic field due to toroid is given as B is equals to mu naught Ni. Same result I am writing, but there is a difference. What is this difference? This N over here is again same, your number of turns per unit length, N, and length over here will become what? So N will be equals to number of turns per unit length of this complete coil. How much it will be? 2 pi r, right? So this is your magnetic field due to toroid. I hope this is clear. The results that you have to keep in mind are highlighted over here. Along with this, some of the points that we should keep in mind. Fine, let us move ahead. Okay, so next we have your Ampere's law. Similar to what we studied in our electrostats Gauss law, Ampere's law is also there. What it says, let's suppose that over here 5 current carrying elements are there, I1, I2, I3, I4 and I5. As you can see, this is I1, sorry. I1, I2, I3, I4 and I5. So as you can see, I1, I3 and I5, the current is coming out of the plane, whereas I2 and I5, the current is going into the plane. We are taking out of the plane direction as positive. That means outward direction is considered as positive. Okay, right? Now, if we want to relate magnetic field over here, in this region, we have this Ampere loop which is enclosing current carrying element I1, I2 and I3, and I4 and I5 are outside. So what does your Ampere's law give us? Ampere's law say that integral B dot dl is equals to mu naught of I1 minus I2 plus I3, right? This is your Ampere's circuital law also said, or Ampere's law. Now over here, certain points that we should keep in mind, that this magnetic field B, which is on the LHS side, is due to all elements, whether it is the current carrying elements are inside the loop or they are outside the loop. Next, on the RHS side, we consider only the elements which are inside the loop, right? So current elements which are inside loop. Now this Ampere's law is used to derive magnetic field. Even your solenoid, toroid, all these results are derived from this Ampere's law, right? So this is our result, keep in mind. And apart from this points also theoretically some questions can be asked, so keep this point in mind. Last, let us look at it, magnetic field due to your current carrying conductor. Okay, so we have come to our last topic, that is your magnetic field due to current carrying conductor. This is also an application of what? Your Ampere's law. The results that we'll be writing over here are derived using Ampere's law. So magnetic field due to current carrying cylinder. Two cases, first of all hollow cylinder, then solid cylinder. One by one we'll take a look. Hollow cylinder. So what is being done is, for outside points, we will categorize the results into two types. That means we'll have two results. For points which are present outside of this hollow cylinder, what is hollow cylinder basically? This hollow cylinder is radius r and the current is flowing along this circumference. The current is flowing, I is flowing along the circumference. So for outside points, let's say that a point P is present which is at a distance of r. Now first thing is outside. Outside means small r will be greater than capital R. I hope this point is okay. Small r greater than capital R, these are your outside point. Now when using Ampere's law, when Ampere's law is applied over here, the result comes out B is equals to mu naught I by 2 pi r. Mu naught I by 2 pi r. Next, for inside points, that is your when r is less than capital R. For inside point, that means somewhere over here point P is present and this inside of the cylinder. For inside points, when we will apply your Ampere's law over here, considering this Ampere's law, when we will apply, there is no current carrying element inside. Therefore, the magnetic field for inside point comes out to be 0. So for outside it is mu naught I by 2 pi r, and for inside it is magnetic field is 0. So these are the two results that we have, right? Okay. Now if we plot a graph between your magnetic field with distance, the graph that comes out is, so this is your B, and this is your small r, the variation from the excess. So till your this r, capital R distance, that is when r is equals to capital R, for inside points your magnetic field is 0, so it will be coming over here. Next, after this for outside points your B variation is inversely proportional to R, so the graph will be something like this, right? That is your B is inversely proportional to R, right? So keep the results in mind and your graph. Fine. Moving ahead, solid cylinder. Solid cylinder, current I is flowing through the cylinder, solid cylinder, and over here the radius is capital R. Fine. Same thing. First of all, we will consider your outside points. Outside points, let's say that a point P is present. A point P is present at a distance of small r, and first is that r is greater than capital R. Small r is greater than capital R. That means it is outside point. For outside points, your result is same. What we had for your hollow cylinder, same result will come. That is B is equals to mu naught I by 2 pi r. 2 pi r small r, so this is your magnetic field for outside point. Well and good. Next, if I talk about your inside point, so some point P is present which is inside of the cylindrical wire, so this is your r less than capital R, that means your inside points. What is your magnetic field for inside point? Magnetic field is B is equals to mu naught I small r by 2 pi capital R square. Mu naught I small r by 2 pi capital R square. Small r is the distance of the point from the axis and capital R is the radius of the cylinder. So this is our magnetic field for inside points, right? If I plot the graph over here, I'll show over here. So if we plot the graph between B and R, the graph comes something like this. For inside points, if you notice, B is directly proportional to R. As your distance will vary, it's a directly proportional linear relationship. As your distance varies, your magnetic field also increases linearly. So the plot is this, right? And this comes on the surface when your R is equals to capital R. The point is on the surface. After that, what happens? Your B is inversely proportional. So the plot is this way. I hope this is clear, right? So these are the results for your magnetic field due to your cylindrical, basically current carrying cylinder. For hollow cylinder, for your solid cylinder. For outside point, inside point, outside point, inside point. This inside point result, keep this in mind, right? Be careful with this. Next is your graphs are there, right? So with this, we have, in this video, we have discussed your magnetic field produced due to current carrying wire in different ways. Due to straight wires, due to circular wires, solenoid, toroid. Then using Ampere's law, your magnetic field due to these cylindrical wires or cylinder is also, we have discussed it. I hope you found the video helpful. All the results which are highlighted, please make sure that you write them properly and keep them in mind. Okay, then, so with this, we'll finish this video. Do consider to press the like button and subscribe to our channel. Thank you very much. Bye bye.